Alright, welcome to another AQA A-Level Chemistry video. Today I'm going to make a video on the part 5 of the series on exam-style questions on acids, bases, and buffers. This is going to be probably the second to last video that I try to make on questions. If it is, then it probably will be the last lesson, but definitely towards the end. I think there's a couple of questions I want to make on ionic product of water, but this should be the penultimate one, and this is going to be a very easy video. I'm going to really try to make this a short video because I don't want to just overextend it. If you've watched the other videos, then this shouldn't be a problem for you. This is going to be quite a simple question, but I did leave a reminder to say for me to remember to do the mark scheme on the previous one. So I say mark scheme just like where the marks are. This is really a mark scheme. I just want to know show you where the marks are. So I did a lot of annotations on this previous one. Again, I'll leave a link in the description to the previous video where I did this question if you want to know about how to calculate the pH with a strong base and a weak acid. So yeah, I did that. So here, if I said the marks, I'd say if I get my green pen out here, the marks, I'd say you get 1 mark for each working out the moles for the sodium hydroxide and the methanoic acid, and then working out equilibrium moles, working out the change in moles there, that's mark 3. This is just all annotation. Again, more annotation here. Obviously, you're not going to be writing it like this in your exam. I just did this video to help you guys out in case you didn't understand what certain things meant. Would you get a mark for? You wouldn't get the mark for the total. Actually, you probably would get a mark for total volume. I think in exams they do give you the mark for the total, working out the total volume. Yeah, you do. So that's how much I mark. That's 4 marks so far. I think stating that the moles of your methanoate ion is 4.5 10 to the power minus 3, would that be a mark? Well, working out these two concentrations, that's a mark, and then rearranging this equation or doing this calculation here, that's a mark, and then getting the correct answer, that's another mark, and working out the pH as being 4.8, that's a mark. So sorry, that's just on that. Okay, so in total, 1, 2, 3. It's just I'm just gonna see if this makes sense. 1, 2, 3, 4, 5, 6, 7, 8. Would this be 9 marks? I don't think they give you. I think they do usually give you the mark for total volume. I'm pretty certain they do. I think it's to here where you wouldn't get the mark for the no. Let's see, so the first 2 are definitely marks. You always get marks for moles. Working out the equilibrium moles, that's another mark. That's 3 so far. Total volume here, you usually do 5, 6. Now, would you get a mark for all of? Doesn't really feel like a 9-mark question. You sometimes get 10-mark questions. I guess it's kind of long. Some of these questions are usually between 8 mark. I have seen 10-mark questions. I'm just saying it doesn't usually strike me as it strikes me more as an 8-mark question than a 9-mark question. But either way, right, it's gonna be within that range, somewhere between anywhere in the range of roughly 7 or 8 marks, just because of the level of the different marks for doing things like simple calculations, like working out the moles. You always get marks working out the moles. There's usually a mark for working out the equilibrium moles, or if you probably don't know what equilibrium moles is, in this case, just the working out the change in moles. I'm pretty sure they give you a mark for working out the total volume, but if they don't, I'm pretty certain from what I remember it does, but if it doesn't, that's fine. But in this video, it's about understanding the steps. This is the steps that you take to get the marks. I've done everything possible to show you how to get the marks, including explaining with other annotations here. But yeah, that's all there is. It's there. So hopefully that made sense. I gave myself here 9 marks in total. I think maybe some of these are 10-mark questions. I don't know, but the point being, it don't matter about how much marks is what and that, but the point being, you understand how to answer the question. So I'm gonna leave that there. I'm gonna actually go on to the video here. So I'm gonna do this little question here. It's gonna be a very simple question. In fact, I actually want you guys to do this by yourself. So pause the video now and try and answer it. All right, so in case you couldn't do that, I'll try and do this for you now. So use your understandings of buffer solutions to calculate the pH of a buffer solution formed when 0.25 moles per dm cubed potassium propanoate with Ka of 1.89 times 10 to the power of minus 5 is added to 0.15 moles per dm cubed of propanoic acid. So the first thing I do here is I write out my two equations, because even though it doesn't give me a mark, I just always do them. Because in case I want to annotate it in the future, it doesn't take me too long to do this at all. Just something, it reminds me of what's going on. It just reminds me of what's going on. Again, and I said before, it doesn't take too long to do these. H2COO minus and then a K plus. And then you understand, obviously you guys already understand where equilibrium is for some of these reactions. You have to write that down, but you should already know by this point that the salt equilibrium is far to the right, whereas for the weak acid is kind of in the middle, very weakly to the right. The next thing here is that I can see the Ka, so I'm going to probably write the Ka equation for this. So the Ka is the acid dissociation constant, so it's related to this the top equation there in relation to acid dissociation. That's concentration of your products over the concentration of your reactants. So our propanoate ion O plus times by H plus over our concentration of a HA, which is propanoic acid. Great. So now I can just see from here, I can actually just clearly see they've given us all the information that we already need. Now, again, I haven't done these questions in a long time, so bear with me. I would have just gone straight to the gone straight to just rearranging the Ka, because I don't need to write all of this. But if you're just someone who's just you're just clueless right now and you're just thinking this is how I go through it from someone that hasn't done this in a long time, I can just clearly see what's going on here, because they've already given me the as soon as I wrote down this equation, I knew exactly what I needed to do, because they've already given me the concentration of our propanoate ion, which is our A minus, and they've already given us the concentration of our HA, and they've already given us Ka as well. The only thing now that we need is the only thing they need to do now is just rearrange the equation. That's it. There's nothing more to this question. Just rearrange this equation. So H plus is equal to Ka multiplied by our HA, which is propanoic acid, OOH, over our A minus, which is our propanoate ion, so CH3, CH2, COO minus. Substitute in our values. So 1.89 times 10 to the power of, make this one a bit more convincing. 1.8, you know what? 1.89 times 10 to the power of minus 5 multiplied by our HA, which is what? What's our HA here? 0.15. Well, yeah, 0.15, sorry. 0.15, and then over 0.25 here. The H plus concentration here is, and that's going to be in moles per dm cubed, because it is our concentration. Put that into our calculator. 1.89 times 10 to the power of minus 5 times by 0.15 mole and over 0.25. 1.13. Now look back to our significant figures here. So we have three significant figures. So I got 1.134 times 10 to the power minus 5, but always write down to three significant figures, because that's the lowest number of significant figures in our question. That's 1.13 times 10 to the power of minus 5 moles per dm cubed. Therefore, our pH is our minus log of our H plus concentration. So, and then just in this case, you just put answer in the answer box, because in your calculator, that's what I would do. 1.13 times 10 to the power minus 5, and then our pH is just equal to minus log base 10 of answer, 4.95. 4.95. Does that make sense? Yes, it does, because we're adding, this is an acidic buffer, so you expect it to be roughly acidic. So yeah, that makes sense. That's that. So the next thing, this isn't a question now, so this answer is done now. The marks for this question probably be like a 3 mark, if I'm being really honest. Get probably a mark for doing that. A mark for working, a mark for either this or this. That's because it's the same thing. You're just substituting your values. A mark for getting the correct H plus concentration, and a mark for the correct working out the pH correctly. So 3 marks there. Okay, so this next thing I want to talk about. So I've in previous videos I've talked about pKa and pH, right, and why they're the same thing. Now this topic is about understanding half neutralization. I want to make this very clear. I've never really encountered this situation in an exam where they've really dug deep in your understanding of half neutralization point, because I don't really think it's something that you should be worried too much about. All you need to know about half neutralization point is just you need to understand what half neutralization point is to understand why pH can equal pKa. That's all it is. Just you need to understand why it is. So here I've got a titration here on the right. And this is we're titrating an acid with a base. So in this base here we've got in this burette here we've got some sort of base, right? So OH minus, right? Let's go back to white color there. And in this here we have our acids, and I've used the phenolphenol purple indicator or pink indicator because we're gonna make it more basic, right? But and we need to it will turn colorless when it's going more basic. But one thing that we need to understand from this, right, is that right way around? Yeah, yes. If it's going more basic, it go turn more colorless. Unless I've got that wrong, I'm pretty certain. Yeah, I'm pretty certain about that. If that's wrong, then go back to the previous video where I explained it. But I'm pretty certain it's when phenolphthalein indicator goes from pink to colors as it's becoming more basic. But anyway, the point being is not that, right? So what is half neutralization point? So you understand neutralization point as being the end point of the reaction. So forget half neutralization. What is neutralization? So this point here where the equivalence point is here, that's neutralization. That's when we consider this is when we consider our H plus in our solution to be equal to the base. All right, that's at that point there's as many H plus as, that's when we have complete neutralization. So then the same as what's the word in chemistry? What's the word in physics that they use? Half-life. The same way how in half-life, if you understand physics, right, half-life is when half of a radioactive material has decayed, because you can't really work out when all of it is decayed. It's a bit random, but you can work out when half of it decays, right? It's not the same principle here, but half neutralization point is just when half of your compound has been neutralized. So it's roughly here, right? Now, understanding half neutralization point is good because we can actually help us with certain calculations. Now, in this reaction here, this is a titration of a acid with a base, but the base is the one that's in excess here, right? This is in excess. So this is in excess, and the HA in this case is our is the limiting factor. We call it the limiting factor because it's the one that's gonna get used up, right? So this is a very simple observation here of a neutralization reaction. Acid plus a base goes to form a salt plus water, and the salt obviously being A minus, because obviously salt's fully dissociated in solution, so it's our A minus, right? But the concentration of A minus, the number of moles of A minus in this, because it's a 1-to-1 mole ratio anyway, right, is determined by the concentration or moles of HA. So however much HA there is, that determines our A minus concentration. The hydroxide concentration doesn't determine it. Remember, the hydroxide is in excess. If we can have as much OH minus as we can, but if we only have one A minus, that's not going to increase the amount of A minus there is, right? So if there's, I could have 1,000. Oh, I don't know why. Sorry, 1 second. I could have 1,000. Just say hydroxide moles of hydroxide ions, right? I know it's very, very small in terms of the entire solution, right? But let's say I just have 1,000 of them, right? I could have one A minus here. So I could have one HA here. That's only going to mean it's going to be one A minus, right? Because this reaction here is when the HA reacts with OH minus, you get H2O and an A minus, right? So the hydroxide ion is one excess. It doesn't affect it. It doesn't affect how much A minus we have. It's just dependent on the limiting factor, which is the HA. Now, I'm going to stop rambling on about things that I've already explained several times already. I'm going to go why, how is that? How does all of this relate to the half neutralization point, right? So if there's a point at half neutralization, right, it should be that at this point at half neutralization, there should be as much, because here, sorry, at the neutralization point, sorry, I'm going to come back because I don't want to confuse you guys too much. So I'm going to go first by the neutralization point. At neutralization, we said that H plus is equal to the OH minus in this case here. Anything more than this, it means that there's more OH minus, right? Because at this point, we would have used up all the H plus, and now we're just adding more OH minus, and that's what causes it to have this massive spike and become more basic, which just makes sense. But it's at the same time, if that's the case, let's say we get to I'm gonna increase the HA now. Let's say we get to let's say 500 HA, 500 moles of HA in our solution, yeah. Just 500 HA molecules in our solution here. That means that if we reach this neutralization point here, we have 0 HA. So the amount of HA we have here at neutralization, HA is equal to 0. A minus is equal to 500. Because remember, the HA is the limiting factor, so it will get used up completely, and our A minus concentration is determined by the HA. So wherever the A minus concentration is at the end of this reaction, it would be the same as the HA concentration at the start of the reaction, or moles in this case, because it's a 1-to-1 mole ratio. So if this reaction goes, so this will fully react. That will fully react. So we know that at half, that's what it means. At half neutralization point, though, so we've made it very clear that this is what happens here at half neutralization. So at half neutralization, this is at full neutralization, by the way, right? At half neutralization, that means that HA, if only half of it has been neutralized, HA is equal to 250 in this case, and A minus is equal to 250, right? So I think that makes sense, right? If only half of it has been neutralized, it means that we have half the amount of HA left, but we've also generated 250 because half of this has been neutralized. Half of that is 250. That means we have 250 we have 250 A minus. That makes sense, right? Okay, so now I'm going to write out the Ka equation. So in this case here, Ka is equal to H plus multiplied by your A minus over HA, right? That's how we understand these reactions. So, because remember, HA dissociates into H plus and A minus, right? So the mass dissociation, which would be the product over the reactants. But if at this point, at half neutralization, HA is equal to A minus at this point here, right? Therefore, in this case here, we know that these two are equal. Therefore, HA and A minus, they cancel each other out. Therefore, Ka is equal to H plus at half neutralization point. Okay, so if we wanted to make we know that's now that makes sense. At half neutralization point, we've just proved that Ka is equal to H plus. Mathematically, scientifically, we know that's the case, right? Again, if I'm going too slowly in my videos, or if I'm not making it as much sense, leave a comment in this video. I'll try to explain it in a way that's better. But I assume that you guys are understanding what I mean here, right? So if we've established now this fact here, Ka is equal to H plus, because we said that the HA and the A minus concentration are the same at half neutralization. They cancel each other out in that case there. So what if we want to work out the pH? Remember, the pH, right, is minus log base 10 of, which is the same thing here, of your H plus concentration. So if we want to do that to the same thing, right? So if we want to work out that, we say minus log base 10. But how do we work out the Ka? It's the same thing. What if we do that to the same thing to the Ka side? If we do minus log of Ka, that gets us Ka, right? If I've just done that to both, I've done that to both sides now. I was trying to work out the pH, which is minus log base 10 of the H plus concentration. But if I do the exact same thing to the left hand side here of minus log the Ka, that's pKa. So now I've just proved that pKa is equal to the pH. So this is why we say pKa is equal to pH, because at half neutralization, HA is equal to A minus. And if I was just to do the minus log base 10 of your H plus concentration, which is what pH is, I was do the exact same thing to the other side, to the Ka, because we know they're both the same thing. pH is equal to pKa, or pKa is equal to pH. And that's all it is understanding here. Now, it's not going to be a question to understand that, but this is just you understanding why we say pH is equal to pKa, because people might say, well, I don't know why that's the case, but that's it. Hopefully this video was helpful, and I'll do one more part of this little series here.